Hi, everyone. Welcome to lecture 9. And today we're going to start talking about random walks, Markov chains, and mixing time. Okay, so, all right. So what are we going to see today? Well, today we're going to see the usual question that we ask: why should we study random walks and Markov chains? And then we're going to talk about the basics on the theory of finite Markov chains, which are the only ones we're going to study in this course. And then we're going to talk about the main topics of today, which are the stationary distributions and the mixing time. And then we're going to just begin to talk about the fundamental theorem of Markov chains. And we're going to complete that in the next lecture. Okay. So, and the last bullet if we have time. All right. So what is a random walk to begin with, right? So a random walk is if we're given a graph G, right, with a set of vertices and edges. So the random walk will start from a vertex V naught, and at each time step, it moves uniformly to a random neighbor of the current vertex in the graph, right? So the next vertex is just, you pick a neighbor uniformly at random and you walk towards it, right? So here's an example where we have this graph, right? So let's say that these are the vertices 1, 2, 3, 4. And we're going to say that the vertices are like the states of our Markov chain, okay? So like we will say sometimes that vertices of the graph correspond to the state of our Markov chain, right? Or let's say a state of a random walk. Let's just put it like that for now. Okay, since we didn't talk about Markov chains, right? So the vertices of the graph are the states of our Markov chain. So if we start here at vertex 1, let's say this is V0, our starting point, what do? Well, from V0, we move to, let's say, well, from 1, right, which is V0, we move with probability half to the vertex 2 or to the vertex 4. And then from 2, we move with probability half. Maybe let me put it, maybe let me draw the execution like this. So we have 1, and then 2, 4, and 3. So with 1, we move with probability half to vertex 2, with probability half to vertex 4. There's an arrow here. And then 2, with probability half, I move back to 1. And with probability half, I move to 3. And at vertex 3, with probability half, I'll move to 2. And with probability half, I'll move to 4. And at 4, with probability half, I'll move to 3. And with probability half, I'll move to 1. Does that make sense? So for instance, one random walk could be, I start at 1, I take a walk, I step at 2, and then at 2, I'll go back to 1. From 1, I go back to 2. 2, I go back to 3. 3, I go to 4, and so on, right? So, but every time I'm picking my neighbor at random, right? And the probability is just, I look at my neighbors, uniformly I go to a neighbor, okay? So, all right. So, all right. So what are the basic questions that we want to study, like mathematical questions that we want to study involving random walks, right? So the questions are, well, the stationary distribution. So the thing is, we may not be able to tell, like, if given a time t, right, what is the vertex that I will be at time t, right? Or sometimes, so we may not be able to say these things, right? Because this is a random variable. But what we can say is that suppose that we take this random walk for a long enough time, right? That's what we're trying to understand. So suppose that the random walk has been happening for a while. Like, can we say something about the distribution, like the probability of being at each vertex of the graph? Does that make sense? So I think the informal thing is, if my random walk has been happening for a while, like what is the probability of being in a given vertex? Right? So that those are things that we're trying to understand. And this actually boils down to studying, like, for example, the stationary distribution, right? Which the stationary distribution will be essentially this question. Well, if we walk long enough, the first thing that we want to ask is, if we walk long enough, does the random walk converge to a stable distribution? Right? Can we say that after that, like, we know what the distribution will be, right? And if it does converge to the stable distribution, what is this distribution, right? And the second question is, well, how long does it actually take for the walk to converge to the stationary distribution? Suppose that the stationary distribution exists, and how long will it take for the walk to converge to the stationary distribution? And when it converges, we say that the random walk fully mixed, because once you have this distribution, it kind of, like, the stable distribution is the distribution that doesn't change, right? So then we say, like, okay, the random walk did all it had to do to achieve that. And this is called mixing time. And we're going to study that later today. And also there's another question, which we're going to see today, which is also the hitting time, right? Which is, so suppose that I start from a vertex V naught, right? What is the expected number of steps until it reaches a vertex VF? Does that make sense? So, okay, so you have two vertices, like the V naught and VF, and you want to know, like, what's the expected number of steps that my random walk will take until I reach this vertex. Okay, and then related to the hitting time, we also have the cover time, which is how long does it take to reach every vertex of the graph at least once, right? So, all right. So these are like 4 questions that we're going to study, and you'll see why they're very natural, okay? And some of them we actually have seen some things very similar to them in previous classes, okay? So here's an example, right? Which we're gonna be coming back over and over today, right? Suppose that we have this graph G, which is the complete graph, right? And A and B are 2 vertices. And remember, Kn is the complete graph. So let's say, let me draw K5 here. So it just means that for every vertex, every pair of vertices, I have an edge between them, right? So for example, this is the K5. And let's say that I have 2 edges, like 2 vertices A and B, right? Okay, so, all right. So now, what is the expected number of steps to reach B in a simple random walk starting at A? Okay, this is the hitting time, right? So this is exactly the question of the hitting time. And for the complete graph, what is the expected number of steps here? So if you remember, well, okay, so if A and B are distinct, let's say that A and B are distinct here, just for an assumption, right? So what is the probability that I go from A to B in a random walk, in this random walk that we have?
1 by n minus 1.
Exactly, is 1 by n minus 1, right? And then all we need to do is to say, okay, well, what is the expected number of steps to reach B, right? Which I'm just going to do like the time that it takes from A to B, right? So this is equal to what? This would be equal to sum over n greater or equal to 1, right? Of the probability that, like, well, I guess we can say like n times the probability that I go from A to B, well, the TAB is equal to n, right? Like TAB equal to n, correct? That's just the expectation. But what is the probability that like this TAB is equal to n? So there's many ways of doing this computation. I'm not going to do all of them. Just so what is the probability that TAB is exactly equal to n?
So like the chance that the first n-1 steps don't reach it, and then the last one does. So like n-2 to the n-1 over n-1 to the n-1.
Exactly, right? So we need the first n-2 steps to not reach it, right? So how will I not reach B? I have to go to any other vertex but B, right? But if I'm at A, I cannot go back to A. So then I have n-2 over n-1 to the n-1 times, and then now I have exactly 1 from whichever like edge vertex I am, I have 1 over n-1. Correct? So, okay, and then we can just compute this, right? And this is great. Or, you know, you could rewrite the sum. Let me just write it like this, and then you can complete the computation here. N times n-2, n-1, n-1 times 1 over n-1. Or you can also just say like sum of n greater or equal to 1, right? Just times the probability that TAB is greater or equal to n. Right? Or, sorry, I think we have to say, like, I think we want to say like smaller than or equal to n. Sorry, no, I have. Yeah, no, it's greater, sorry, greater or equal to n, my bad. Right? Because the probability that A, like, what is the probability that TAB is greater or equal to n, right? This sum here is exactly like sum of the probabilities of TAB being equal to K for K greater or equal to n, right? So if you do this double sum, you get exactly the same sum as above. Does that make sense?
Yeah.
All right. And now, well, how can we rewrite the sum, right? Like, so another way of writing the sum is just like sum n greater or equal to 1. Now, what's the probability that TAB is greater or equal to n? Well, to be greater or equal to n, I have to fail for sure my first n-1 attempts. That's all, right? So if I fail my first n-2 attempt, it's like I have n-2, n-1, right? Which is the probability that I fail. And this would be equal to what? I have to just fail n-1. Does that make sense? Sorry, there's a, my bad. I have 2 n's here that are competing for attention. So let me say that this sum here, like, because n is the number of vertices, so let's say that this is k. So my bad. Then we have k, and this is n-2, and this is k-1. Sorry, I just realized. And then this is n-1. Sorry, the last one was n-1. So let me just fix this right now, right? Because the sum is k, and then so k-1, and the probabilities involve n, right? Does that make sense? So sorry, and then let me put, instead of k here, let's put j. Let me just fix it online already. This is k-1. Okay, now it's better. Because the n just depends on the graph, right? So I'm sorry, like the complete graph has the n. Okay, so is it clear so far? Okay, so this is the expected number of steps to reach B, right? All right, and okay, and then starting from and it's here, you know, if you compute this, right? Like, what is this sum? Let me just compute it so that we can see that we could have derived it in a different way, right? Like, so what is this sum? This is going to be exactly 1 over 1 minus n minus 2 over n minus 1, which is equal to what? N minus 1. Does that make sense? So, okay. So now let's just think about it for a second. Well, the answer is pretty simple for us to kind of have done all these calculations, right? So, and why is that? Is because if you think about it, like what is the expected number of steps to reach B? Like if we start from A, let's say if A is different from B, we can think about this as the balls and bins problem, right? Because suppose that I have n minus 1 bins, which are all the vertices of the graph except A. For now, let's just think for simplicity, right? Like if every time I have one bucket there, I'm saying, okay, I want to reach bin B, right? And I throw a ball like independently, right? Into this n minus 1 boxes, what's the expected number of steps that I need so that actually there is one ball in bin B, right? That's exactly n minus 1, right? Because every time my success rate is 1 over n minus 1. Does that make sense? So we should have thought, we could have thought about it in that simple way as well, right? So, but anyways, so that's one result that we already saw before, kind of. And now, starting from A, what is the expected number of steps to visit all the vertices? Right? So this is the cover time that we're not going to discuss today. So let me just, for the sake of time, not cover it, but this is a great practice problem. Let me leave that as a practice problem which we can discuss and in office hours. Practice problem. And not only we're not going to discuss that, but the idea is actually that you have seen this before. You have seen this before under a different name. Okay, so if you think about it, you will guess. We saw this problem, exactly this problem, or a problem that is very closely related to this problem in previous lectures, right? So actually, can anyone have a guess?
The birthday problem?
Sorry?
Well, not birthday problems, like the cereal, the thing with the cereal boxes, right?
Correct. So that's the coupon collector, right? So we saw the coupon collector problem. All right. So, and the question here as well, is there a stationary distribution for the complete graph, right? And the answer is yes, right? And what is the distribution? Well, the distribution will be like the vector 1 over n, 1 over n, 1 over n, right? Like the uniform in this case. Right? Because once you go from the point A, from vertex A, you kind of are almost uniform, right? Like, and then as you keep going, you will tend to this uniform distribution. And we're going to prove today that this happens, right? And you can see that this is a stationary distribution, right? Why is this stationary? So let's say, like, if this distribution is pi, and if you think about it, if I have this distribution, if I'm uniformly distributed among all the vertices, once I take a step, what happens to my distribution? It becomes the same. And why is that? Let's say what happens. So what is the probability of being at A, at a vertex A, at time t, given that I was uniform at time t minus 1? What is this probability? How do we compute it? So I'm uniform already at the current time, right? So what's the probability of me being at a vertex A at time t?
Is 1/n.
1/n. But how do you find this value 1/n? Why is it 1/n?
Like it's gotta, like, if you add them all up, it's gotta be equal to 1 because it's gotta be at one vertex, and since vertices are like, ambiguous, then they should all
Right.
be the same.
Right. So like the argument, it goes through symmetry, right? But the formal argument that you can exactly, like there's a symmetry, right? If I'm uniform in all of them, the graph is symmetric, so it should be 1/n. So that's your intuition, right? Like, but how do you prove it? You can say, well, like it's just exactly the same thing as, like, let's go through all the vertices I equals to 1 up to n, probability of being at A at time t. Let's say that this is like xt equals to A, given that xt minus 1 is equal to I, correct? Because the way the random walk is that to go for time t, I only care where I am at time t minus 1, right? So, but what is this probability? Well, this probability is equal to what? If I equals to A, this is 0, right? So in particular, this is the same as like 0 plus, for all the other vertices, like sum of I different from A, I have exactly the probability of what is the right. So what is the sorry, yeah. So probably if I was uniform at time t, right? Sorry, I forgot to write the second part here, right? Which is the probability of me being x, like x t minus 1 equals to I, right? Because I'm saying if I'm uniform, I know that this probability, first of all, is 1/n, right? And then now, what do I have? Well, let me copy this as well. Let me erase. So this is 0 if the vertices are the same. And then it's also, I can just complete now by saying this is the sum, like 1/n, which are those probabilities, times the sum of the probability. What is the probability now that if I'm in I different from A, that I go to A, is exactly 1/n minus 1, right? For each of them, because we're in the complete graph. But then I'm summing, this sum is exactly equal to 1. So I get 1/n. Does that make sense? So if I had probability 1/n at being at A at time t minus 1, then I'm gonna still have probability 1/n of being at, like, if I had this distribution at time t minus 1, I will have the same distribution at time t. Does that make sense? That's why this distribution is the stationary distribution, right? So, okay, there's one. Is there another one? So the answer, as we'll see, is no. Okay, so this is the only stationary distribution. Okay, and mixing time, well, let's talk about mixing time later. Okay, so, and as we discussed, right, like, so as a practice question, compare this question to the cover time to actually the coupon collector problem. Okay, so, all right. Now, if you noticed from our computations from the previous slide, right, the random walk is a special kind of this stochastic process, right? A stochastic process is just, some probabilistic process. It's just a fancy name. So, and here, if you think about it, if I start at vertex x0, and let's say that the variable xt tells us is the state of random walk at time t, right? And state here, remember, state is just a vertex, right? Like vertex in the graph that I am at. So if you think about it, the random walk is a special kind of stochastic process because, well, here you could say, what's the probability that xt, right, where I am at time t is equal to some vertex vt, condition on all the history, right? So this is all the history. Let me kind of move this around. So this here is all the history. But if you think about it, the random walk ignores most of the history, right? So random walk only cares where we were last. Does that make sense? So the random walk is this very special kind of stochastic process, because you could have thought that, oh, knowing where I was in time 0 initially would affect where I am now, right? But I mean, it will certainly affect where I am now if I just follow the process. But the thing is, probabilistically, it doesn't matter, right? Like where I was initially to dictate where I'm going to be at step t. The only thing that I care about, that my process, the only thing that my random process cares about is where I am currently. That will determine where my neighbor will be, correct? So, all right. So now, and that's what we just said, right? That the probability that we're a vertex vt at time t only depends on the state of our process at time t minus 1, right? But now, this is a very special kind of stochastic process, right? Because what it says is that this process is kind of forgetful, is memoryless, right? Because the random walk is like, oh, what did I do, like, 4 steps ago? It doesn't matter. It doesn't affect what I'm going to do now, right? It has no effect, right? So a Markov chain is actually characterized by this property, okay, by this forgetfulness property here. Okay, so that's, and this process, I mean, it happens, it appears everywhere. So it is very important or to study this Markov chains, okay? So, all right. So why, right? Like, so why study Markov chains and random walks? Well, first of all, Markov chains and random walks are ubiquitous in randomized algorithms. Okay, so they show up everywhere. And for example, as we're going to see in next lecture, the page rank algorithm is a random walk. Right, so it will be a Markov chain. And now, oh, sorry, yeah, I have to, maybe I'll say the page rank algorithm is a random walk. Okay, so there is some finer details on why it's not Markov chain, or Markov chain as I'm defining here. You could probably define like inhomogeneous Markov chains, but let's not get into much details. Okay, so but they appear in page rank algorithm, which you all know, and it's quite useful. And it appears in approximation algorithms for counting problems. Okay, so for example, if you want to compute the permanent of non-negative matrix, which is kind of one of the ultimate counting formulas that we have in combinatorics and in mathematics in general. And also it appears in sampling problems. Okay, so Gibbs sampling, for example, in statistical physics, right, is a Markov chain, and in many more places. Okay, and also it appears in amplifying probability of randomized algorithms, probability success of randomized algorithms without using too much randomness. Okay, so because as we saw, remember, when we want to amplify the success probability of an algorithm, one way that we can do it is we can just run multiple copies in parallel, correct? But one problem with that is that we take randomness for granted, where randomness is quite difficult to generate. So like true randomness, right? So then what you want is randomness is a scarce resource. So you'd like to kind of do this amplification process, but you want to do it without using too much randomness, right? So, and there's a way of doing it by doing random walks on expander graphs. And again, as the red highlights, indicate, those are amazing final projects. If you're interested, I'm happy to talk to you in office hours. Okay. So these are some places, and there's many more places where Markov chains and random walks appear. Okay. And all right. So now let's represent finite Markov chains. And what is a finite Markov chain? Is that we just have a finite set of states, okay? And that's what we're going to study today in the next lecture. So if you think about it, as we saw in the first slide, a Markov chain can be seen as a weighted directed graph, right? Because if you remember over random walk, like the random walk that we had before, right? Like 1, 2, 3, 4, what happens? I went from 1 to 2 with probability half. I went from 1 to 4, probability half, and then 2 to 3, probability half, 3 to 4, probability half, and then here I went 4 to 1, probability half, 2 to 1, probability half, and so on, right? So we have this graph, probability half, probability half. So you can see that this random walk can be seen as a directed weight graph, which is exactly the Markov chain graph, because if you notice each edge, like this edge, is exactly the edge that says probability of going from 1 to 2 is a half, is encoding that probability. Does that make sense? Okay. So, okay, and again, like a vertex is a state of the Markov chain, right? And the edge ij corresponds to the transition probability from I to j. Does that make sense? And this, like, so the Markov chain, we saw first a random walk, but as we can see, like the Markov chain, it was just characterized by this property, right? Like, so probability that, well, the Markov chain is just characterized by what is the probability if I'm at I to go to j, because the only thing the Markov chain cares is where you are now to take your next step. Does that make sense? So we saw a random walk, and now we're seeing that, oh, finite Markov chains can be represented as a kind of a random walk, right? Except that now we allow, like, instead of being an undirected graph, we have to be in a directed graph. Because, for example, this could be a random walk, right? So we have, let's say, two states, 1 and 2. Let's say let me put my states here, 1 and 2. Here's another random walk. I go from 1 to 2 with probability a half. Let's say that I have 3 here. 3, I go to probability a half. Now 2 just goes back to itself with probability 1, and 3 goes to 1 with probability a half. So this is also Markov chain, right? Because now from 1, I can go to 2 with probability half, or I can go to 3 with probability half, right? And then from 3, from 3, I can go to 1, or I can go back to 2, let's say, with probability half. So now we have all the probabilities. Does that make sense? So this is another random walk. Yeah. So each arrow corresponds to a directed edge. So see that now the edge is corresponding to a tuple, right? Not a set. So the other order matters. Okay. All right. So now the thing is, we say that a Markov chain is irreducible, okay, if the underlying directed graph, so if you forget about the weights, just look at the underlying directed graph without the weights, this graph is strongly connected. What I mean by strongly connected, there's a directed path from I to j for any pair I, j, and v. Okay, so for example, here's the example that I gave before. If I have 1, 2, 3, right? If we just looked at the underlying graph, okay, yes. Is this graph strongly connected?
Yeah, 2 is in a different component.
Sorry?
2 is in a different strongly connected component.
Exactly, right? So 2 is in a different strongly connected component because from 2, I cannot get to anywhere but 2. Does it make sense? So this is not, so this is reducible. Oh, sorry, 1 second. My program closed. Okay. Okay. Right. So this is reducible, right? But another one that we saw that was irreducible was the random walk 1, 2, 3, 4. And then here we had that random walk that we drew before is strongly connected. Right? Because here you can just take a cycle one way, a cycle the other way, and that covers everybody. Okay, so there's a difference here. And also, like if your graph is disconnected, then it's certainly reducible, right? So because even the graph was already disconnected to begin with, like even if you make it undirected, right? So in general, we're going to assume. So in general, we're going to assume that the graphs were given, they're connected. Okay. So all right. So all right. So now there's another way to represent the Markov chain, right? And a Markov chain can also be represented in weighted adjacency matrix format. Okay. And what is that? Well, so here's the thing, right? Let's draw our matrix. So let's say that we have the first Markov chain, like 1, 2, 4, and 3, right? And then here we had our Markov chain with the transition probabilities like half for everybody. Like half. This is the Markov chain, right? So we can represent this Markov chain with a weighted adjacency matrix. How would it be? Let's say that P here is the matrix, is going to be like a 4x4 matrix, like 1, 2, 3, 4, 1, 2, 3, 4. And now in the entry ij, I'm going to put the probability of going from I to j. So if I go from 1 to 1, I get 0 here. 1 to 2, I have half. 1 to 3, I have 0. 1 to 4, I have half. 2 to 1 is half. 2 to 2 is 0. 2 to 3 is half. 4 is 0. 3 to 1 is 0. 3 to 2 is half. 3 to 3 is 0 and is half. 4 to 1 is half. 0, half, 0. Does that make sense? So here, Pij is the probability. So Pij is the probability from going from I to j. Does that make sense? This is how you represent the Markov chain as this weighted adjacency matrix format. Okay. So, all right. And that's what we said, right? So entry Pij corresponds to the transition probability from I to j. And now here's the thing, right? So what we can say is we can also have PT is a probability vector. Okay, so little p of t, which p of t is the probability of being at state I at time t. So let's just say that we have this probability. So at first, so for instance, if we start, if our Markov chain like starts at vertex or state 1, we have that PT, right? P naught, let's say P naught is the beginning, right? So P naught of 1 is going to be equal to 1, and P naught of j is going to be equal to 0 for all like j bigger than 1. Does that make sense? So that's just saying that, oh, I'm starting at, this vector, right? So in particular, like P naught would be like E1, which is the vector 1, 0, 0, 0. Okay, so that's one example of probability vector, right? But then, well, what happens to once I have P naught, how can I compute P1? Well, P1, right? So what's going to happen is that the transition from one state, from one time to another time is given by what? Well, the new probability, the probability at time t is going to be exactly equal to the probability, probability of being at the probability vector at time t plus 1 is equal to the probability vector at time t times my transition matrix P. Does that make sense? Because how can we see that, right? Let's just see how to compute this. So, and the computation is simple, right? So PT plus 1 of, let's say, A is equal to what? Is equal to the sum of I equals to 1 up to n of PT of I times the probability of going on from I to J to A, correct? So maybe let me say J here. So J, and then we have I, and then here's the probability of going from I to J. But now what is this? This is exactly Pij, correct? So if you think about it, if you think about the sum, this is exactly if I take the vector PT, right? So this is a vector, and then I multiply by my matrix P, and then I take what? Well, this is a vector, and then I take the entry J, correct? Does that make sense? Okay, so then this is our representing how we can represent the finite Markov chain and the transition of states, right? Like it's just a matrix vector multiplication. Okay, great. So, all right. So now we saw already one property of a Markov chain, right? Which is being irreducible or reducible. And another one is the period of a state I, right? So the period of a state I is the greatest common divisor of all the exponents t, okay, such that of all the times t, so you should think of t here as the times, right, like at the time, such that the probability that I go, so if you think about this one, this is the probability of starting at I and being back at I at time t. It's exactly this, right? So what we're saying is that the period of a state is the greatest common divisor of all the times that I started at I ran my Markov chain for t steps, and if I had a probability non-zero of being at I again, then we say like we take the GCD of this and this is the period. Does that make sense? I look at all the times that I'm back at I, right? Because if this probability is positive, what does it mean, right? So if you think in terms of the graph, if this probability of I in t is positive, what does it mean? It means that in t steps, there are t steps of my Markov chain that form a cycle that goes from I back to I. Does that make sense? So there's a cycle of time t. So this period is the greatest common divisor of all the cycles that I have of all sizes, right? Like, so you take the GCD of all the sizes and then you have the period. Okay. So great. So now note that the period may not necessarily be always one, as the following like random walk or Markov chain, right? Like that we had. We just look at the random walk of this graph, which is a Markov chain, 1, 2, 3, 4. Note that at even times, I will be at 1 or 3. And at odd times, I will be at 2 and 4, right? If I start at 1, right? So if I start 1 at even times, I can only be at 1 or 3. And at odd times, I can only be at 2 or 4. Does that make sense? So the period for 1 is exactly 2, right? Because 2 is there, and I'll only be back at 1 in an even number. I have to take an even number of steps. Does that make sense? So this is an example where, you know, you could have period like equals to 2. And more generally, right, well, so what we say as well is the state is aperiodic if its period, its state I is aperiodic if its period is 1, right? Okay. So, and now we say that a Markov chain is aperiodic, okay, if all the states are aperiodic. Okay, so if there's one state which is not aperiodic, which has a non-trivial period, then we don't say that a Markov chain is aperiodic, right? So is the Markov chain is aperiodic if all of the states are aperiodic. Okay,
It's the same as saying that it has a self loop, right?
sorry?
The state has a self loop. Is this the same as saying that?
No, it's not the same as saying that, right? Because like you can have not a loop and
Right.
still be aperiodic,
Yeah.
right? Because all you need is the GCD of all the times. Okay, but that's a great question, but it's not the same as having a self loop. But as Ryan is saying, if my Markov chain has a self loop for every vertex, then obviously is aperiodic because in one step I could be back, right? So that's one way. That's usually the trick that people do to random walks to make them aperiodic, right? Is you do a lazy random walk. Okay, so okay, that's a good observation. So all right, now for example, you can see the bipartite graphs, they will yield periodic Markov chains, right? And in particular, we actually have seen already the example of a bipartite graph, because if you look at this graph, well, we can represent this graph as a bipartite graph, right? So I can just have 1, 3, 2, 4. This is the same, right? So actually this graph was the bipartite graph here, right? Like was a complete bipartite graph in like 4 vertices, right? So, okay. So, okay, and now here's the lemma. Okay, so for any finite, irreducible, and aperiodic Markov chain, there exists some time t, okay, some finite time t. So whenever I write t less than infinity, I'm just saying that t is finite, okay? So this is just like finite, such that we know that the probability of, so if I take the matrix P and I make transitions like t steps, right? Like p to the power t, and then I look at the entry ij, okay? So this is going to be bigger than 0 for any ij in V, for any 2 vertices, and for any t greater or equal to capital T. Okay, so there exists this finite t, okay, this bound, such that its probability is bigger than 0 for any t. Okay, so and this is just saying, okay, and the only thing we need is that the Markov chain is finite, irreducible, and aperiodic. Okay, and if you want to see a proof of this, you should see the references to chapter 4. Like in this book, there's a reference to where the proof is. Okay, so okay. All right, and as we saw before, so maybe we could see like, I mean, let me just draw the example again. I guess I drew the example before. So, but again, we know that this random walk is periodic, right? So 1, 2, 3, 4. So we already went over it. All right, and well, we already went over examples of reducible Markov chains. So I guess this is the first part of the lecture. So